exception there. But you've got to keep that rhythm and that order and start off recognizing what do I have so I know where to start.
Can you do the multiplier with subtracting at the top right now, or do we have to
We really do have to, yeah. I would say I will go ahead and solve these and post them probably before I even leave for the weekend. So if you want to treat these as extras, so take a look at that and then just email me, we'll talk. Okay. Yeah, I don't want to get too rushed on equations because this is major. Okay, so, all right. So we're going to now switch gears into solving equations. Everything we've dealt with so far in this chapter, with the exception of introducing rational functions, f of x equals, a function defined by a rational expression. And we can evaluate that if you know f or f of x, plug it into the right place and evaluate. Or looking at that function, we can find its domain. We can find out all the things that x could be and all the things x can't be. Remember, on a function, you find the restrictions in the domain. Remember what that graph looks like. That's the vertical asymptote. It's that dashed vertical line that the graph will never touch. So that's what restrictions mean on a function, on the graph of a function. So that was the beginning of 10.1, but after that, like I said, we pointed out, we've been dealing with expressions. Simplifying, multiplying, dividing, adding and subtracting expressions, and mixing it up with complex fractions. Okay? 4 basic operations plus just simplifying, putting in lowest terms. Okay? Here, though, we're solving. Now we're solving. Before, we could not tell you what x is, because there was no equal sign, we couldn't solve anything. We're just putting it in simplest terms. But here, we're solving rational equations. We're dealing with equations. And an equation is some expression, like we've been dealing with, equal to some other expression. That's the basic definition of an equation. You set an expression equal to an expression, you have an equation. And you would then have enough information to solve for your variable, solve for x. Now, your expressions might be any type of expression. You might have linear expressions or higher degree polynomial expressions like quadratic and cubic. If these are all linear expressions, you'd solve using your linear strategy, your addition and multiplication properties of equality. Get x on one side, c on the other. X equals c, x on one side, a number on the other, by adding and subtracting the same thing to both sides and dividing away the coefficient. If your expressions are polynomial, higher degree polynomial, like quadratic or cubic, that's what we just had the test on. You put those in standard form, move everything to the left, equal to 0, factor completely, and then use your zero factor property. The degree tells you how many factors you'll get, and each factor gives you a solution. Now we're going to be doing equations where one or more of our expressions are rational, which is just a polynomial over a polynomial. So it's going to be on the left will be some polynomial, some rational expression is equal to, and I'll just use different letters to show us a different expression, r over s. So one or more of our expressions will be rational. There could be any combination of this. There might be one rational, and there could be things plus and minus, other rational or non-rational. Okay. But then if you have at least one rational, you have an equation with at least one rational expression, then you have a rational equation. Okay. Now, you cannot solve rational equations, but you're going to do it. By killing the rational equation, you're going to, let me not use such harsh words, I'm not going to kill it so much as you're going to transform it. The first step you do is going to change a rational equation, which you can't really do much with. It's going to change it into a polynomial equation, which you know how to deal with. The polynomial equation you're going to transform it into is either going to be linear or quadratic. So you may end up with one solution or two, depending on the polynomial that is created when you destroy your rational equation. So, the basic list, if you look on the back of this expressions notes, here's the basic list, summary of the rules for solving equations. Okay. And we're going to walk through each of these as we go through some examples. But here's the basic overview, the basic idea. The first couple of steps that we do are going to look exactly like what we do when we are simplifying a rational expression with addition or subtraction. Okay. It'll look exactly the same, but then it's going to diverge. Then we're going to do something different because we are going to start off by, and I didn't even write it on here, but just like we did, just like I pointed out here, here's your problem. This is an expression you're simplifying. Spread it out, lock things up and factor, and leave room. That's going to be the same first step we do here, and then we're going to find the LCD. So just like we wrote it, spread out, locked up and factored, and then once we did that, we can see our LCD. We write our LCD. First step's the same, but that's where things diverge. Because we're not going to use our LCD in the same way. This was that example from 10.2. Our LCD was used and not discarded. We made every denominator we have match that LCD, and that LCD was part of the final answer. It didn't get thrown away. You started with these rationals, and you still have a rational at the end, unless things canceled out to flat. But basically, you have whatever your numerator is, you put it back over your LCD, and that's your answer. Okay? The LCD wasn't thrown away. You made it match, and then cleaned up the numerator to put over it. We start here by factoring our denominators, locking them up, factoring, writing them nice and spread out, and then using that to find our LCD. But then what we do with our LCD is different. Here we have to keep our LCD when we're simplifying an expression. With equations, we're going to use the LCD to kill the denominators. Does that sound familiar? Like we do with linear equations? When you have linear equations with fractions, first job, kill the fractions. How do you kill a fraction? You put the LCD over 1, right. You're not giving everything a common denominator. When you solve linear equations with fractions, you didn't want to make more fractions. You didn't want to give everything the common denominator, so you have more fractions with common denominators. That didn't do you any good in an equation. Your job was to kill the fractions. The LCD helps you do that, but you didn't use the LCD like you didn't give things the LCD. You used the LCD over 1 to wipe out the fractions and flatten your equation. What you already know how to do with that, with linear equations killing fractions, is exactly what we're doing with rationals. We're putting our LCD over 1, and we're killing the denominators. We're going to flatten out our rationals. We're going to turn our rational equations into a nice flat polynomial equation. Okay. So rather than giving everything the LCD like we do when we have to do when we simplify expressions, we're going to multiply every term by the LCD over 1. We use the LCD, not to give it the LCD, but basically what you'll hear me refer to it, I'm a very peaceful person, honestly, but for some reason I use very violent language with math sometimes. We're going to weaponize this LCD. Okay? We're going to use it to destroy our rational equation. We're going to use it to transform our rational equation. Okay? So the LCD is not going to be made to match, but rather we put it over 1. That weaponizes it so that when we multiply every term by it, it's going to flatten out the equation. Okay? It'll cancel it out. Now, once you do that, you're going to have either a linear or you're going to have a polynomial left. It'll either be linear, which you solve with your general strategy, just solve for x, one solution, linear, first degree, one solution. Or what you have left will have a square or a cube. I'm just going to stick with squares for right now, but it could be any degree polynomial. Okay? So, for our purpose, it's just quadratic. In which case, I've got a square, it's quadratic. I have to set it equal to 0, put it in standard form, factor completely, and use your zero factor property. You'll have 2 solutions. Each factor will give you a solution. Okay? Now, the one difference here between this and linear equations, once you find that LCD and put it over 1, before you move on and do this, there's another thing you need to do. You need to note your restrictions. That sound familiar from 10.1? Okay? That was for functions, the restricted domain of a function. Here, we're not writing a domain. These are equations, not functions. Single variable equations, so we don't talk about it as having a domain so much as we do have things that x can't be. There are things that x can't be because it would make part or all of our rational equation undefined. So anything, before we move on, we set our LCD equal to 0 because the LCD is just made up of all our individual denominators, so anything that makes any part of the LCD equal 0 means it would make some part of our equation undefined. So we're going to find restrictions. We're going to find what x cannot be. Okay? And then when we finish solving, we see what our x's are. If any of those x's violate the restrictions, they get thrown out. There will be perfectly good solutions for this polynomial. We'll get all of our possible solutions by solving this polynomial, but some might have to be thrown out because they violate the original rational that would make it undefined. Okay? Okay, so that's the very wordy overview. Let's put this into practice. Because what comes next, whether it looks complicated, simple, or complex, is going to follow, keep this by your side, this set of rules in this order. Okay? So, given the problem, 2 over x minus 5 plus 1 over 2x equals, we're solving an equation, 5 over 3x squared plus, minus 15x. Now this is an equation and the directions told you to solve it. Okay? So we're going to use a common denominator. We see addition and subtraction and all. We're going to use a common denominator, but we're not going to give everything a common denominator. Okay? We're solving for x. We're going to flatten this thing out. This first step, I strongly encourage you to follow the model that I'm showing you. Any factoring you have to do, any other pencil and paper work in factoring, do it away from here. Off to the side, or if there's not room, on a different piece of paper. Okay? Keep this area clean and chaos-free. Your next step should be to rewrite this problem, period. Any other sort of anything, but you're going to have it all factored and locked up. So any factoring you can't do mentally, do it off to the side. And I'm going to leave room. Now I'm not going to extend my bar because I'm not going to be tacking on my LCD, but I'm going to leave room to put my LCD over 1. So I'm going to rewrite this problem, 2 over x minus 5. Now can that be factored? Now, if it could have, I should have factored before I wrote it down. It's linear, no GCF, but I am going to lock it up. Now, I'm going to leave some room. I'm spreading it out. This is the tree-hating stage of the problem. When you get past this long, tedious, ugly, keep it as clean and chaos-free as possible, but tree-hating stage, all of a sudden you're going to have a nice, flat, clean problem, and you'll go, I can handle that. Okay? Get past this one step, and then you're good to go with stuff you already know how to do. So I'll write 1 over 2x. There's nothing to factor there, nothing to lock up. Leave some space, equal to 5 over, now can I factor that? Yeah, what can I, it's definitely not linear, but what should I check for first? 3x, leaving behind. Yeah. So everything is factored, clean, and locked up. Now the numerators, lock them up if you need to, don't in this case, but don't factor them, don't multiply them. If there's distributing or factor, don't do it. Just lock them up if necessary. But it won't be mathematically wrong if you do something to the numerators, but you're just going to have to undo it later when you clean up your one big new numerator. So don't make more work for yourself.
Why won't you use, like, if there's a greatest common factor?
Uh-huh.
Why don't you use the 2 parentheses? And how sometimes, like, in some problems, instead of doing that, we use the, like, x minus 5 parentheses and x plus 5.
Oh, like the conjugates?
Yeah.
Well, that's if we had to factor a difference of squares, for example. So your denominators might be anything you have to factor. This was just factoring a GCF. If you had something, you're going to see an example next where one of your denominators is a difference of squares, so it factors into conjugates. We'll have another example where it's an a equal 1 trinomial, so it'll factor into 2 binomials with ACB. Yeah, your denominators might require any type of factoring you know how to do. Yeah, in this case, it just required a GCF. Now, before I move on, I've got to first find my LCD. And when you've done this step, your LCD is right before your eyes. Okay? You write down every factor you see. Now, first look for things outside the binomials. Got 2x and 3x, right? Okay, so since it's 2x and 3x, first let's deal with the numbers. 2 and 3. What would a common denominator be for 2 and 3? 6, right? Okay. So just treat those as if they were just plain old numerical denominators. The denominator of 1/3 and 1/2 would be 6. Okay. But they also, unlike the earlier problem that had the 2 and the 3, these also have x's. So what do I write here? X. Yeah, not x squared though, right? No, I see an x, I write an x. I'd only write x squared if I had x squared in one of the denominators. Yeah. If I had x squared or x cubed, whatever, the highest degree of x's would be the in the LCD. But doesn't matter, one here, not one there. It's only at most once in any one denominator. Now I look at my binomials. What do I see?
X minus 5.
Right. X minus 5. It appears here and here, but not there. Doesn't matter. At most, it appears one time in any one denominator. No other binomials. That's my LCD. Okay? Now, this is where we diverge. All of this was basically the same as if this were an expression we were simplifying. The only difference is we would have written longer bars here. But factoring, locking up, cleaning, leaving space, LCD, now we diverge. Because this LCD, we're not going to give these this LCD. This is the big thing where I see people make mistakes. You're doing the problems on the test. If this were just an expression, we'd give everything matching LCDs, set it aside, clean up our numerator, put it back over the LCD. No, equation, solving, killing the rational, transforming the rational. So we're going to weaponize our LCD. We're not just making it match, we are putting it over 1. Now it is a weapon to flatten out our rational. But before we move on and do that, one other thing we need to do. We can do it at the end, but people who leave it to the end tend to forget to do this. Okay? The next thing we're going to do is we're going to find our restrictions. So we know at the end if our solutions are good or not. We need to find any value of x that would make any of these denominators 0. If any of these 3 rational expressions is undefined, then the whole thing's bad. Okay? So our LCD is a combination of all of our denominators. So if we can find what would make the LCD undefined, then we know we're good. We know something about all of our denominators. Okay? So our LCD is already factored. When we found domains in 10.1 last week, you first had to factor your denominator, and the degree of the denominator told you how many restrictions, right? Okay? So you would factor it. If it was a degree 3, you get 3 factors, 3 restrictions. If it was degree 2, 2 factors, 2 restrictions. Linear, 1, no factors, 1 restriction. In this case, our LCD, because of how we created it, is already factored. How many factors does our LCD have? 2, which means we have 2 restrictions. Okay? Our restrictions, the things that x can't be, are set each of our factors not equal to 0 and solve for x, in this case, cannot be 0. And our other restriction, the other thing that would make the LCD, which accounts for all our denominators, the other thing that would make this LCD equal 0 is if x minus 5 is equal to 0. This is 0 factor property. If this is 0 or that is 0, then the whole thing is 0. And if anything makes this 0, then it would make at least one of these 0, and so it would be bad. And so x minus 5 cannot be equal to 0, so x cannot be equal to 5. Those are our 2 restrictions. So we just set those aside, and we'll check back at the end to make sure our solutions are good. This is still where all the work is. Writing it spread out, cleaned up, locked up, factored. We can see our LCD. The number of factors in that LCD, we've weaponized it over 1, and then the number of factors in that LCD gives us that number of restrictions. And now we're ready to deploy that LCD, flatten it out, see what we have left, and solve. So 6x times, it's always times, 6x over x minus 5 over 1. 6x over x minus 5 over 1. This is a step that can be so messy and so long and take up a long, all the way across your paper. But you do this one, and the next one will be like, oh, that's a breath of fresh air. That is a relief. It will just get flat and pretty, and you will recognize what you can do with it. Now, just like killing fractions with linear equations, these are just ugly fractions. You are canceling out diagonally. You should be able to cancel out the entire denominator. If you can't, then something went wrong with the LCD. So I physically diagonally strike out my denominator and whatever matches it in my LCD. Now really this is multiplication, so whatever's left and not canceled out is going to be multiplied times your numerator that was there, but you're not touching that numerator right now. Okay? Now 2x cancels out and so does 6x, but is anything left behind? A 3, right, because 6 over 2 becomes 3 over 1, right? The x is x over x, the x is gone. So it's just if you put 6x over 2x, you get 3 over 1, and the x's would cancel out altogether, and the binomial remains. Here, the binomial cancels out, and so does the 3x and the 6x, but is anything left behind on top? Yeah, 2, because 6 over 3 is 2 over 1. The x's canceled out, and the binomials canceled out. Now, just like I encouraged in other situations before, this step, you're going to lift off your numerator. Don't try and do too much mental math when you do this. If there are any parentheses, don't distribute or FOIL mentally. Okay? Even if you're really, really good at it, I'm good at it, I make a mistake here. Okay? Just lift it off, and then you'll see how flat it is, pretty, clean it up, and solve. Now I need basic multiplication. 2 times 6x would give us 12x, so that's fine. And then plus 1 times 3 times x minus 5. I'm not going to try and do that distribution mentally. I could, but I know that's where I make my careless mistake. So I'm just lifting it off right now. Equals 5 times 2, and everything else canceled out. Oh, that's much prettier to look at, right? Does this look like it's going to be linear or quadratic? No. Do you see any exponents? No. Now, sometimes with parentheses, depending on what you're multiplying when you distribute, you might actually end up with an exponent. Okay, so kill the parentheses and make your final decision. But your job now is to either solve a linear or quadratic depending on what you have. If it's linear, you're solving for x using your general strategy. If it is quadratic, you want to start as you clean it up, make sure everything's on the left and zeros on the right.
I have a question.
Uh-huh.
Do you think when you simplify everything turned out to be 1 at the bottom?
Yes.
Will it always be like that?
Always. That's the whole, if it didn't, then you didn't kill the fractions.
Okay.
That's the whole point of choosing this LCD, because this LCD incorporates elements from all of the denominators. So whatever's down here will cancel out. You just might have something left behind on top.
Okay.
But you'll always have ones on the bottom all the way across, and you can drop those.
Okay.
Yeah. Yeah, because your LCD is a product of all your possible denominators. It's going to incorporate all the denominators. This will cancel out. You just may have something left. On top, though. Only on top. That's what flattens it out. All these ones on the bottom just get discarded because they're not necessary. Now I distribute, FOIL if I need to, whatever I have to do, kill the parentheses, combine like terms, and decide whether I'm just solving general strategy linear, one solution, or whether I'm putting it in standard form because it's quadratic, factoring, and getting 2 solutions. Here I got 12x plus 3x minus 15 equals 10. Definitely linear. So I got 15x, and I'm going to add 15 to both sides, so it's equal to 25. Okay. Linear strategies. Distribute, combine like terms. Combine like terms here, added 15 to both sides because I'm keeping the x on the left, push the number over to the right. Basic addition properties of equality. And divide away my coefficient, giving me x equals, always put in lowest terms. Do not write this as decimal. That would be a repeating decimal. And then you'd have to round it to write it or use the repeating bar. We can't do math with that. Keep it in lowest term fraction. Now, before I put that in set notation and walk away, is this a good solution?
Yes, because it doesn't.
Is that one of the restrictions?
Right. I can plug this into my this is absolutely a good solution to this linear polynomial equation. That doesn't mean it's a good solution to my original rational, but it doesn't violate a restriction. If I did plug it into my original one, it would not make anything undefined. I don't have to plug it in to find that out. By finding the restrictions, I know that. And so it's good. Put it in set notation.
So if it was part of the restriction, I mean, yeah, if you did have a restriction, we just put no solution.
Yes. In fact, or if you have 2 solutions, one might be bad or both. It depends on what you have. We're going to see a variety of that now. Okay. All right, so 1 over x minus 4 equals 8 over x squared minus 16. Remember, your first step is just to rewrite the problem. Okay? But when you rewrite it, spread it out and make sure all the denominators are factored and locked up. Make sure numerators are locked up if necessary too, but don't factor the numerators. Here's a case of one of my denominators is the difference of squares, so it factors into its conjugates. Now that it's all factored and cleaned up, I can see my LCD. My LCD, what factors do I see?
X minus 4.
And? Right. Doesn't matter that x minus 4 is in both of them and x plus 4 is only in one. Doesn't matter. If I see it, it's in my LCD. Now, do any of these appear more than once in any one denominator? No, so you don't need any exponents. Now I'm going to weaponize it, because I'm not going to be making these match. I'm weaponizing it so I can kill those denominators that are there. But before I move on, how many factors in my LCD? 2. How many restrictions? 2. One of my restrictions is x minus 4 cannot be equal to 0, and my other one is x plus 4 cannot be equal to 0. So x cannot be equal to 4, x cannot be equal to negative 4. And you can see, for example, 4, if my solution were 4, 4 would make both of these undefined, because there's x minus 4 in both of them, and make both of them undefined. If it were negative 4, it would only make this one undefined. This one would be fine. That would be negative 8 on the bottom. That's fine. But it doesn't matter if it makes everything undefined or just if it makes even one of your expressions undefined, then it's out. Can't be used. Right? That's why the LCD covers it all, because the LCD is a conglomerate of all your, it represents all of your denominators in one. All right. So let's put that LCD to work. It is always the case. Boom, your denominator is gone, and you just also cross out whatever it matches. Something will be left on top, but nothing but 1's left on the bottom. Something may be left on top. In this case, nothing's left on top or bottom. Nothing on bottom like it should be, but it also all cancels out on top.
So it's 4.
Yeah, exactly. What I'm lifting down here, this is all 1 on the bottom, so I've got 1 and then times x plus 4 is equal to 8. Oh, wow. How beautiful is that?
Better.
Yeah, right? We went from to no problem. So, of course, there's nothing to distribute there. It's just x plus 4 equals 8, or x equals positive 4. Right. Now, before I put that in set notation, declare that the solution and walk away.
You can't.
Yeah. 4 would make actually both of these undefined, because it violates our restrictions. Okay? Therefore, because that was the only possible solution, it is the correct solution to this polynomial. Our solutions to the rational will be among the solutions to the polynomial, but some might have to be thrown out. In this case, there was one solution to this linear polynomial, and it was a bad solution for the original rational. So since there's nothing else, no solution. Don't say prime. Some people are getting mixed up. Prime is just for expressions. If you can't factor an expression, you say it's prime. If you can't solve an equation, then you say no solution or null. So either one of these is fine.
Or what?
Null. Yeah, this is the null symbol. We call that null.
All of them?
Huh? Okay. So 2 plus 3 over x is equal to 2x over x plus 3. How many terms do I have in this equation? 3, right? Are they all rational?
No.
Right. Only 2 of the 3 are rational. As long as there's at least one rational, it's a rational equation. That doesn't mean every term is going to be rational. However, when you write this, your second step here, your tree hating step, make sure anything that's not rational, write it in rational. How would you write this in rational form? Just put it over 1. Yeah. Anything that's not already up, just put it over 1. That way everything will stay lined up. 2 over 1. Nothing to lock up or factor anything there.